I'm kind of interested in the my research career. In fact, not my instrument science career, is about the interaction of technology with the environment. And this is some work that was sponsored by the CNRS during a sabbatical in the University of Paris-Saclay in Orsay. Some of you might know that laboratory. But what I'm going to talk about today is what happens to polymer science when people are finished with it. And we've talked a lot about new materials, but this is a very old material, and it's it's a subject of a lot of debate, and I think it's important for both scientists to address this debate, but also the general community. This comes from a website from the Ellen MacArthur Foundation, and it's really looking at the solution to this problem, and that's what I'm talking about today, how we solve this problem, because it is a problem in terms of recycling. And what we'll find out as a result of the discussion today is that recycling isn't really an option for polyethylene-based materials. I've been working in polyethylene in a variety of industrial contexts for some time. And what I'll be mostly talking about is the kind of packaging. But I'd just like to draw your attention to, there are a lot of polyethylene-based materials, and each of them requires specific thought. This is a material, you may see these going around Europe. This is a polyethylene-based tank that is used for transporting chemicals, things like corrosives. It's a great product. This is a very, very strong fibre. It's found as waste in the ocean quite a lot. I also have a history of contributing a lot to the waste of polyethylene in the environment. This is a product that we worked on. It's for an agricultural application where you put seeds underneath this line of polyethylene. It acts as a small greenhouse, and the seeds come up quicker. It keeps in the moisture. And of course, for example, in Australia, when the weather gets hot, one wants this to fall apart. And we had a product with extremely good degradative properties. It would degrade when the sun got hot. And we did quite some work on this. And as a result, there's many tons of plastic in the environment. What I'm mostly going to talk about is the kind of materials that you use for packaging. So these are very flexible. They need to be cheap, and there's a lot of them. They're transparent, and they have extremely good barrier properties. The kind of polymers that are mostly used in this application are PET and the polyolefins, which I'm going to mostly talk about polyethylene. It's kind of ironic for me, when I did my PhD in cellulose, or about 25 years ago, there wasn't quite so much plastic packaging, and the use of environmentally, the use of cellulosics was seen as a huge environmental problem, and today we seem to be going back to those. So let's just think about the problem. There's a lot of work, there's a lot of stuff in the media at the moment, and this is from a magazine, Teen Vogue, that maybe not so many of you read, but the take-home message really is about the public perception of how this material is in the environment, is that it keeps breaking up into smaller and smaller bits, and it's there for almost eternity. And one can really see the emotional impact. And this is another, well, it's not quite a popular science article. It's written by some biologists, and their perspective on this is the damage that this kind of material causes to the environment. And the other take-home message from this article here is that there's a huge amount of, in the accounting for what's gone into the environment, there's a huge deficit in what's there. And these people say that they find it on the beaches, but I'll argue that something quite different and not quite so environmentally harmful has happened to it. So the aims of this work, first of all, I really want to understand the fundamental processes which determine the lifetime of polyethylene in the environment, and in this case, specifically the marine environment. I believe that this kind of information will allow us to develop mitigation strategies for waste that's already there, and how much money or resources we should devote to this problem. But to look further into the future, what kind of packaging we need to design to mitigate the environmental impact. So as I said before, this work was sponsored by the CNRS and the University of Paris-Saclay. I did most of it while on sabbatical there. In the last year or so, I've been working in Lund, and this is the publication that has resulted from this work. And I refer you to this because this is a really nice piece of work. The plastic samples that I'm mostly going to be talking about have been taken from this place in the Caribbean. My colleagues from Toulouse were instrumental in collecting these, and we've furnished rather a nice story from what we've learned from these. So first, the thing about the materials. As I said before, my colleagues went out with nets and collected little bits of plastic, and to a large extent, many of these pieces, it was really impossible to discern where they came from. They've been mixed up thoroughly in the North Atlantic Gaia, and most of them had come from, you know, somewhere in Europe, I would guess. There were some of these debris that we found that we could actually relate to packaging that we brought back in Paris. And I'm not going to talk so much about this until the very end of the talk, but it's very important to understand that these materials, as they're left in the sea, begin to oxidize. And of course, as they oxidize, they turn into carbon dioxide. And this, of course, without any man-made intervention, becomes the eventual place where they end up as carbon dioxide. So let's think generally about milk processed polymers, also, and in general about the milk processing of consumer thermoplastics. This is a polymer, of course, and you melt it, and you put that liquid into a structure, and you allow it to cool down, and that can be your packaging, whether that be a sheet or a bottle. This lamellar structure, so the stringy bits are the polymer chains, and what happens is it crystallizes incompletely. Complete crystallization is, of course, thermodynamically stable, but this state is frustrated by the length of the chains and the entanglement of the chains. And what you're typically left with is this lamellar structure. And each of the experimental techniques that I will talk about today has a particular perspective on this lamellar structure. So small angle X-ray scattering gives you a very simple measure of the repeat unit structure in that. That's the lamellar and the region of amorphous material. I'll talk about wide angle X-ray scattering, which will look at information about the packing of the polyethylene chains in the lamella themselves. And an important piece of information was from not chemical Raman spectroscopy, but more physical, where we look at low frequency modes and use that to measure the distance or the thickness of the lamella, or the distance that the chains are packed within the lamella. It's important to note that this lamellar structure is very critical for this important barrier property of these kind of materials, the fact that oxygen doesn't diffuse in so easily. The first observation that we made was that the thing depolymerizes as it's left in the sun. So on the right hand side here we have the new boxes, and here's on the bottom on the X scale is the molecular weight, and we have the cumulative weight fraction. You can see as they're aged, they become smaller in molecular weight and probably, or definitely, more polydispersed or dispersity. And what one can imagine is that the UV light and other chemical processes are cutting the chains. We also see an increase in the carbonyl content, as I mentioned previously. But this is effectively a release of this kinetic frustration to the crystallization of these materials. And this was the starting point that we came from. We knew this was happening, and we wanted to understand what physical changes this very fundamental process caused in these materials. So I'll start off with the wide angle scattering. Typically, the wide angle scattering of these materials was quite complicated. There was a lot of fillers in there, a lot of inorganic components, but we focused on two crystallographic reflections, the 110 and the 200. So that's this one here, the big one and the little one. And underneath that, there's a broad amorphous halo. And we fit 3 peaks to that, one for the amorphous halo, one for the 110, and one for the 200. And we extract the following pieces of information from this. First of all, the width of these Gaussians reflects the coherence length in a direction normal to that crystallographic plane. So here I've done some pictures of, it's a bit more complicated than this, the strings I have here of polyethylene molecules. And so there may be some tilt in the polyethylene in the lamellae, but we're measuring a distance within this plane here. And what we see as the materials get older or have been experienced more weathering, as the reflections get broader in both cases. So these dimensions are getting smaller. We also see that the degree of crystallinity, which is the relative intensities of the crystalline versus the amorphous peaks, becomes less. The materials become more crystalline as they're exposed to the environment. And that's not surprising given this very simple model of kinetic frustration. So from the wide angle scattering, we also did some DSC, which confirms this view, that we see the materials become more crystalline and have smaller crystallites, which basically means there's more smaller crystallites with the aging. The SACS results were really quite astonishing when we came to it. We thought, well, this material is becoming much more crystalline and we may see some growth. So this is the unit cell, if you like, for this lamellar structure. You can see one peak and maybe a second peak there. I plotted it here, intensity versus Q multiplied by Q squared against Q here, and you can see the position of the peak much more clearly. You can see there is second peak, but it's not a terribly ordered peak. There's no third order peaks as one might see in a lipid lamellar system. But you can see with aging, the intensity of this peak goes down, and with the highly weathered materials that we couldn't really say where they came from, but just from the fact that they were polyethylene, we could see that this peak had almost disappeared completely. These are the two extremes. For some of them, there was a little bit of lamellar structure there, but by no means the typical lamellar structure you see in new material. And what this is saying is that as well as the domains, as well as the crystallites, more crystallinity, that these domains are getting smaller from the wax, but also this coherence length, coherence is disappearing as the lamellar structure is being diminished. And just for another perspective on this, so the two perspectives that I've mentioned so far, wide angle scattering and SACS, don't look directly at the packing of crystalline chains in the lamella. And to understand whether these were getting longer or smaller, we looked at this longitudinal acoustic mode, which is a collective mode in the polyethylene chain. So it's an accordion motion. And just to give you a context for this, this is an actual spectra. So here's the laser line, and one is looking at, very, very small Raman shifts. One can use this shift to directly measure the length. So the longer the accordion, the smaller the Raman shift, the shorter the accordion, the larger the Raman shift, and we see no change at all. So this infers that there's no growth of these lamella in this direction along the normal to the lamella. So this is a simple story that's come out of these three simple measurements, and of course some other supplementary measurements which confirm the story, that in the sunlight and in the ocean, that we have this process where the chains are cut by UV or some kind of chemical reaction. What this does is it leads to release of this kinetic frustration of to the further crystallization of these lamellae. We see that from the SACS, that this lamellar structure is broken apart. We see the disappearance of this, this correlation peak in the sacs, and we see the domains in the plane of the lamellae from the wide-angle X-ray scattering becoming much smaller. And so the overall picture is that in the microplastics from the ocean, this lamellar structure has been broken apart. Now, if we think about how these things, how long they last in the environment, oxidation is an extremely important process. So for the lamellar structure, the diffusion of oxygen, and this is well established in the literature as well, is effectively stopped by this lamellar structure. And so the oxygen cannot get as far into the bulk material. In the material that's been in the sunlight, this lamellar structure is broken apart, and even in this cartoon view, it's easy to see or visualize that it's much easier for oxygen to diffuse into it and oxidize it. So that is to say that the physical processes catalyze the eventual photooxidation of these materials, and which is to say they probably won't last in the ocean. They probably won't be getting smaller and smaller, and this is probably the reason why we don't see so much very small pieces of polyethylene in the ocean. Now, I've given this simple cartoon view of how oxidation of polyolefins is catalyzed by the physical degradation. But the other take-home message from this picture is that polyolefins have a useful lifetime, or in terms of recyclability, and this is limited by chain scission. If one has smaller and smaller molecular weight components, of course, they're going to crystallize on much shorter timescales, and this means that in terms of their mechanical properties, they won't be stable, and this is a fundamental problem with recycling polyethylenes indefinitely. And so I think these issues really need to be thought through, both in terms of what kind of materials we use for packaging, but also where we put resources into remediating the obvious problem with the amount of polyethylene in the environment. Just to think a little bit further, so what I've done here is I've compared polyethylene with some other polymers. Cellulose, it's been around for a long time. Polyhydroxybutyrate is one of these bacterial polyesters, and there's some really nice work being done on these, not just this particular polymer. It's really quite easy to produce in various biotechnology situations. In fact, I've recently worked on people that have produced thermoplastics just by bacterial action on pig waste. And you know, the product wasn't very commercially attractive, but I think there's a lot of work that can be done in this space. So this particular polymer has very similar physical properties to polyethylene, but its mode of degradation is really quite different. It does suffer from photodegradation, but it also is able to be eaten by other microbes, and the loss of mass is really quite fast compared to what one sees with polyethylene. Cellulose is really quite a different material, and it has some issues around recyclability, but I think that, as I'll come back to the bigger picture in terms of the carbon cycle, it's a much more attractive proposition. So to think about this, and this is not to say that recycling is not a viable alternative for other materials, but in terms of using polyethylene, I think that this is a little bit of a dead road, because the materials that produce from recycling are really not that useful in terms of making new materials from milk processing. I'll finish the talk with a sort of a wider view on this. So when we actually originally started this work, we were thinking of polyethylene crystallizing and becoming more resistant to chemical reaction And of course, eventually it will go back into the fossil pool. And probably we kind of joke that in millions of years, people might be seeing fossils of packaging rather than fossils of trees. But this is the kind of perspective that I think we need to use to think about these issues. Cellulose, on the other hand, is produced by photosynthesis, of course, and it's a direct way of taking carbon and using it in materials. And even though the trees get chopped down, it's a little bit of more of a closed loop, whereas the partitioning of carbon from which is originally dug up or pumped up from the fossil pool is really quite a different situation. So with that, I'd like to thank you for your attention. I hope that's given you something to think about. I think these are important issues for people to deal with in it, both scientists and non-scientists, and it's important to have these discussions. And I thank you for your attention, and if you have any questions.
All right.